progress. Hello everyone. In this webinar we're going to talk about equipment, common setups, regular vibration tests, and we will make a first start guide. This topic is really important because we have a lot of new customers who want a quick guide to vibration testing. We're hoping to make this webinar interesting and worthwhile. And the first thing I need to talk about is equipment for vibration testing. The common set consists of a vibration controller, a shaker, an amplifier, some set of sensors, and of course your testing object. Today we will go through all these equipment parts and discuss their selection algorithm. Our first step is to select our controller. Here in the screen you see all our controller range, all controllers in our product range, and we will discuss all of them. The first one is RULA-21. It's our basic vibration controller. Here you see that it has 2 outputs and 4 input channels. Also, it is scalable, so you can connect 8 controllers together and get 32 input channels and 8 outputs. This controller supports all features from sensor calibration to all kinds of vibration tests. The next controller is RULA-21M. It's the modified and improved version of the previous controller. It has 2 modifications with 4 inputs and 8 inputs. It has a higher sample rate, and it has an ability to connect temperature sensors. And our largest controller in the range is RULA-25. It's the biggest one, and the key feature is that you can change its modules. We have 3 modules now, 1 module with 4 output channels, 1 module with 8 input channels, and we have a strain gauge sensor module. So now you can connect multiple controllers of this type and get up to 512 input channels. And now we are developing the improved version of this controller, and I think soon it will be possible to get 1000 channels. Here you see the comparison table of all our controllers. Here you see the channels per unit, their frequency range, their sample rate, all sensor types which can be connected with this controller, and the main function. All these controllers can be used for vibration testing, the data acquisition, and sensor calibration. And the selection of the controller depends on the number of channels you need to collect data from them and the frequency range of your tests. The next topic I want to describe is shaker selection. All vibration shakers can be divided into 5 groups. The first one is like electrodynamic shakers. I think you all are familiar with them. The second one is servo-hydraulic. After that, we have modal shakers, and the most interesting ones are drop machines and shock shakers. Electrodynamic shakers have middle and high frequency range. They're used with high acceleration values and low displacement. And their main usage is regular vibration tests, non-shock tests. After that, we have servo-hydraulic shakers. They are used in a low frequencies range. They have high displacement values, and they are used for all kinds of shock tests, and if you have a huge testing object. you can place it on the hydraulic shaker. After that, we have model shakers. They're used for model analysis. They can impact an object during the model analysis, and now we are developing this feature in our software, and soon we will have an option to influence our object from model analysis module. After that, we have drop machines. I talked about them in the previous webinar. They're used for replication of real-life shock and for durability testing. And shock shakers are the best solution for shock tests. They have high acceleration, high displacement values, and they are really good for replicating shocks. And now let's talk about the main rules for shaker selection. When you select a shaker, you need to compare the frequency range of the shaker with your test, because you shouldn't run the test at lower or higher frequencies than in the passport of the shaker. After that, you need to calculate the maximum load mass. For this, you can use this formula, where the m is the load mass, a is acceleration, and f is the force. You all are familiar with this formula, and it's really easy to calculate the maximum mass for your test and your shaker. After that, you need to use the appropriate shaker for the test. For example, you should use shock shakers for shock tests, model shakers for model analysis, and some kind calibration shakers and really accurate shakers for calibration. And after that, you need to set up cooling system for the shaker if it's needed. Now we will talk a little bit about our amplifiers. In RULA, we have a range of 3 amplifiers: a RULA 200, RULA 500, and a RULA 1000. They all have overheating detection, overcurrent detection. They all control maximum current, and here you see all the amplifiers, and they all can be used for model analysis and work with electrodynamic shakers. And the most interesting part is the sensor selection. All measuring sensors which can be connected to our controllers can be classified by 2 parameters. The first one is their channel type. A sensor can be charge, IP, voltage sensor, strain gauge, and TEDS. And we can also classify them by measurement dimension. We can classify them by acceleration, velocity, displacement, force, strain, and temperature. I must mention that strain gauge sensors can be connected with our regular RLC21 and RLC21M with our strain gauge amplifier RLS39, and for our RLC25 we have a special strain gauge module with 8 channels. Now let's discuss all kinds of sensors we can work with. The first one is accelerometers. They can be piezoelectric or MEMS. We work with all of them. Also, we can work with laser displacement sensors. You can use them in case you have a low frequency range in your test, and they can measure low frequencies and high displacements really nice, and they can be used in our resonance testing module. And we have a special test type which is called fatigue. In that case, you can use displacement sensors for controlling the system. Also, here you see our model analysis system, and here on the bottom of the frame we have a force sensor, and it was really nice to use a force sensor during the model analysis because we have a high load mass, and in that case you can get really good results. Also, as I mentioned, some of our controllers can use temperature sensors like PT1000 and Type K thermocouple. We can show the temperature data in our software and draw some graphs. And here, as I mentioned earlier, on the right side, you can see our strain gauge module and our strain gauge amplifier, and on the left side it is a regular strain sensor. Do we have any questions?
So yeah, we do actually. So the first question is there any kind of warning on a channel overrange on our controllers?
Yeah, now we have this option. It was developed in the maybe this release or previous, and now we can detect an overrange on our RLC21 and 21M controllers, but in RLC25 this feature is under development now. And I think now we continue, and I don't see any questions. And now let's talk a little bit about sensor mounting. Here you see a regular accelerometer. It can be placed with in multiple ways. The first one and the most basic is a stud. You screw it to the shaker stable or your testing object. I'll use a stud today. After that, you can use wax mounting. You can have a magnetic base or electric isolation base. Personally, I prefer a stud, and sometimes when it's really difficult to place a sensor on your testing object, I use glue. And now some words about sensor selection rules. You need to select a sensor according to the maximum acceleration during the test. You can use this formula. For example, you have a sensor with sensitivity 100 millivolts per G, and we know that in maximum voltage on our channel can be 10 volts. We divide the sensitivity for 10,000 millivolts and get our maximum acceleration value. After that, I need to say that, for example, you have a shock test, you know that you have high displacement values, and for this, I recommend to use low sensitivity sensors. And for such tests as calibration, it's better to use high sensitivity sensors, for example, 1000 millivolts per G or something like that. And now we will go to the most interesting part of our webinar. I'll make a first start. Here in the screen you see our configuration. I have a PC which will be connected to our RLC21 controller. After that, I'll connect it with an amplifier, with the shaker. After that, I'll place an accelerometer on our shaker, connect it with the channel of the controller, and we will run some basic vibration tests. Let me check my webcam. I think you can see my setup now. And now I'll show you the process. Here you see our Velox 21 controller. Here I have a power socket. I take a power cable and insert it here. After that, I take the second cable and connect it with our input. Then I need an Ethernet cable and insert it in our controller. And after that, I need to insert our shakers cable. We're using Fibra B5110 shaker today. So the back side is connected. Now, Ethernet better. After that, I take one regular VNC cable, insert it with the first out of our controller, and connect it with the amplifier. It has a VNC connector that is backside. After that, we have a sensor. It needs to be mounted on the shaker. It's a regular IP sensor with sensitivity of 10 millimeters per G, and screw it into the shaker's cable. Like that. After that, I take the cable, connect it with the sensor, and connect it with the first channel of our controller. And now we're ready to turn on the system. After that, I need to say some words about our amplifier. It has an overcurrent level selection. You need to press stop button for some time. And here you see the setup menu. Here you can set the overcurrent level.
Could you show it to the camera a little bit closer?
Like that.
Yeah, that's good.
I'm using the gaming mode. I'm set it at 1.7. After that, I press stop again and save the settings. Saving is completed. The device is restarting. After that, I set the gain mode to the minimum level. And now we can use our amplifier. And our next step is to set up our software. I'll go back to my PC. Here we have our execution file. Let's run it. And before we start, we need to check our network card. To do this, I prefer to use Windows plus R combination and execute ncpa.cpl. Here we have all our network cards, and today I will use my Ethernet card. After that, I go to Properties and Internet Protocol version 4. Here I see that now my card obtains an IP address automatically. I need to change this feature to this and enter the static IP address. something like this. After that, I click on subnet mask and apply the settings. Let me double check it. Yeah, it's okay.
Could you also mention the function of the stop button of the controller?
Yeah, during the test, if you made some mistakes or the test gone wrong, you can manually stop the generation process on the controller or the amplifier. You press the stop button and your system will stop generating signal. It's really useful when, for example, you started in a vibration test and finally understood that you missed some channels, or for example, you had an AP and a charge sensor, and some engineers replaced them, and in that case, it's really useful. It saved me many times.
Yeah, and I mean, like, how do you get the IP address of the controller?
The IP address. Okay, we have another function which is which can be used with our stop button. Here on our controller, press stop button, and you can see a serial number, an IP address, and the subnet mask of the controller. This is really useful when you have a stack of, for example, 5 controllers, and you need to check the IP addresses, their connection. And finally, now we can run our execution file.
Yeah, I need to mention also that once you get the IP address of the system, you just set the IP address in your network card to any other address. So, for example, if your controller has an IP address of, say, 9, then you set it to anything other than 9. So any other free place.
Yeah, your network card IP address must be different from your controller's IP address. Here, during the installation process, I press next, and I'll install it to the basic folder. Let's wait a bit during the installation process. And I must mention that after the setup, we have a special program which can automatically configure your network card, but I prefer to do it manually. But you'll see a window, and if you press that you want to configure your network card, you can select it, and it will be set up automatically. Let's wait some time. And do we have any questions?
Yeah, so somebody asked about the TED sensors. So do we support them, and which templates are supported?
Yes, we can work with TED sensors. We support TED's accelerometers and microphones. We use template 25 and 27. And I think this feature is really interesting and can be used during your tests.
I think we have another one about the shakers we work with. So which brands of the shakers do we support?
I think it's a question for you.
Okay, so we actually work with a lot of shaker manufacturers around the world. So pretty much any manufacturer that is present on the market. So mainly, I think Tira, Spectra, Danlabs, Donling. So we support any type of electrodynamic electrodynamic shakers. So if your project needs it, we'll be able to suggest a good option.
And here you see the network card configuration. I configured it manually, so I press no. You need to press OK here. some system registration. And after that, the system will ask you to find the controller and to update it. Let me double check my network card. Something gone wrong and my settings missed. Okay, we got some troubles with my Ethernet connection, but I'll show you this option when we start the software. So here we can press close.
Yeah, so we actually have a question, yes, from one of the viewers. So how do we check whether a shaker will be able to execute a vibration profile? What are the parameters checked and how they are interlinked? So I guess
it's a good question. I'll show you it in software. We have here, we finish our setup and let's run our software. I'll close the first start window. We will select our report creation. And after that, about the shaker. Here in configuration tab, we have a shaker database option. You press it. Here you can see all the manufacturers. For example, let's select our shaker. Here you see the shaker's frequency range from the passport, its maximum object mass in kilograms, and we have 3 columns. They are called limit values. We have limit values for sine tests, random tests, and shocks. You set the maximum acceleration peak value. After that, you set the maximum velocity for the shaker and the maximum displacement. I must mention that displacement here is set in 0 peak, not in peak. After that, you see force and maximum driving voltage. You set these parameters according to the shaker's passport, and when you select this shaker during the test profile creation phase, all these parameters like acceleration, velocity, and displacement will be checked automatically. And on the in the bottom of the window, we have a special tab which is called limit values, and they can be 3 colors: red, yellow, and green. If it's yellow, you don't exceed your maximum limits, and you don't exceed 75% of the limits of your shaker. If it's yellow, you can run such tests, but I must mention that you are really close to the maximum limit. And if it's red, I don't recommend running such tests. You can damage your shaker, and you must be really careful.
Yeah, could you also maybe show the slide again with the calculation of the profile? In the formula.
Here you see, for example, check the maximum load mass. You created a profile. You know that you have some kind of fixed force. It's set in the shaker's passport. You know the maximum acceleration value during to your profile. You can see it in the bottom of the profile creation tab. And if you divide this fixed force by this acceleration, you'll get the maximum mass of an object which can be placed on your shaker during the test.
So the same person also requested to describe the driving voltage concept.
I don't understand the question. Let me read it again. I think maybe it's about the output which goes to our shaker and the data from the control accelerometer. And if I'm correct, we generate some signal to our output. It goes to our amplifier, which will be increased up to our level which we set with the gain knob. After that, it goes to our shaker, and all the data is gathered with our accelerometers. And after that, it goes to our controller, and it's being analyzed there. We have all kinds of stop conditions. For example, if you exceed the maximum acceleration, velocity, or displacement, or get an overrange on the channel, or get some kind of cable problems, the system will automatically stop. And the maximum voltage which can be collected with our input channel is 10 volts, so you can recalculate, get the maximum acceleration as I showed here in the slide. You know your sensor sensitivity, and you know that the maximum voltage on the channel can be 10,000 millivolts. In that case, you can get the maximum acceleration value, which can be got with your sensor. I think that's all about this. And if I didn't answer some of your question, you can write us, and we will try to answer it in the email. And now I think I can continue in our software. So today we are going to run our basic sine test. We select sine, and let's create a test. We will run from 40 Hertz up to 400 Hertz. Our amplitude will be 1G. We will create a linear profile. And here, as I said earlier, you will see all the limit values. For example, let's apply the settings, and you see that during this test, you'll get a maximum acceleration of 1G. The velocity will have this value, and we will get this displacement. After that, you can check the profile on the fly option. In that case, that when you enter the profile, it will be checked automatically, and you'll get limit values on the fly. And if you exceeded some limits, you'll see it immediately. After that, let's go to schedule, and here we have run profile command. We have in Sine, we have a sweep. We can run from starting frequency to the end frequency on some kind of level. We can search for resonances. We can make cycles with commands. We can pause the test, hold frequencies, create reports, make stepped sweeps. But today we are going to make a sweep from 60 Hertz up to 200 Hertz. We will skip resonance search, we're not doing it, and the step-by-step test. We will go to control. Here you see all control settings which can be used during the test. We had a webinar about the sine theory, and all the settings were described there, but today I recommend you not to change the settings if you're a newcomer with vibration tests. After that, we go to limits. Here we see that our shaker is selected, and here you can set the load mass. After that, here you can enter the maximum output voltage, voltage to acceleration ratio for startup and running the test. And we have notching limits. It's a useful feature. It can be used for controlling some different parts of your object when the sensor which is placed on them exceeds limits. After that, we go to channels, and here we need to change our configuration. We open channels configuration window. Here we have 10 millivolts per G IP sensor on the first channel. We press OK. And we're not using all other channels, so we will disable them. And let's apply the settings. And I want to say about our controller, if you have an APE sensor and you missed and selected the wrong type, you'll get a red LED over this channel. It's a really useful feature, and all used channels will have green LEDs over them. And I think now we can run the test. And before we start, I need to set up gain on the amplifier. I'll set it to 15%. And now we're ready to run the test. Here we see that we started the test successfully, and here we're getting the data from our accelerometer. As we selected in the schedule, we're running from 60 Hertz.
And could you comment a bit maybe on the lines we have? So the colors.
Here we have a line which is called channel 1. It's the data from our accelerometer. Also, we have a shaker line. It's the limits from our shaker. Our limits from the table is shown here. All of them are calculated into acceleration. And if our signal exceeds this line, we'll stop the test automatically. Also, we have a task line. It's shown here in green. It's our profile line. Also, we have tolerance and aborts. That means if we go over this line, which is called tolerance, or this line. Here in the test progress, you'll see a message that you exceed the tolerance level. And if we go over abort level, the test will stop automatically.
Yeah. So the question, another one, what is the amplifier gain right now?
We have 15% gain.
15%, okay. So you need to mention that, of course, you change it based on the profile.
Yeah, and your shaker, your needs. Sometimes you can even run it at 100%, but I never had such cases. I regularly run my tests at 40% gain, 20% gain, or something like that. And for example, when the collaboration module was developed, I tested all the algorithms at 5% gain.
Yeah.
Not to damage your testing object or shaker and your sensors. And now we can talk a little bit about another test type. It is called random test. Here we go to test settings, and we will run from 100 Hertz. We will increase at 300 Hertz, and we will run up to 1000 Hertz. Let's apply the settings. And here in this tab, you can recalculate your profile. For example, here our maximum acceleration is about 4G. I want to run the test at 2G level. So I entered here, press recalculation, and the amp is recalculated and you get these values. After that, the main command for random is run. That means you'll run this profile for the desired amount of time. Let's set it to 30 seconds. After that, we go to limits, see that our shake is selected. Here you see, as in sine test control limits, here you set abort and tolerance for all the profile. And here we see our new feature limit spectral lines, but I think it's not for newcomers. Maybe we will make another webinar about random and I will describe all the features in details. After that, here we need to select another channel configuration. We changed this one. So here you see that on the first channel we have 10 millivolts per G IP sensor and all other sensors are disabled. So we apply the settings and run the test. The main graph for random is spectrum density versus frequency. And let's open oscilloscope. And set it into spectrograph mode. Now we will start up. And here you see that we are increasing the level at these frequencies. And I think maybe you can hear our random test.
Yeah, also one more question. How do you determine how many channels you need? So how many input and output channels you need while selecting the controller?
For example, you have some kind of small object which will be placed on your shaker, and you know that you run the test or using only one single shaker. That means you need only one output channel, and after that the number of sensors depends on your needs. For example, you have some object with different parts. For example, you know that some parts are weaker. You place, for example, one control sensor on the shaker's table, one sensor on the left side on some kind of parts. Also, take another sensor, place it on the in the bottom of the object. And I think the best example is a regular metal ruler or a beam. You can fix it in the way both ends go over the shaker. In that case, you need three sensors. One of them is placed in the center of the shaker's table, and two other sensors are placed on the ends of your beam or metal ruler. In that case, you'll get not influence signal to control the test from the sensor in the shaker's table, because it won't get and catch any resonances on this beam. And using two other sensors, you'll see all the resonances, all the impacts on different frequencies, and the sensor number depends on your object and on the number of shakers you are using. For example, for multi-shaker tests, when we have at least two shakers, you need two outputs. And now we can run with 8 shakers at the same time.
Yeah.
It's our the biggest number of shakers for multi-shaker tests now, which can be run at the same time with good results.
Mm-hmm. So we also have a question about random test. How many random values a shaker selects while running random profiles? Is there any parameter? Is it the DOF?
So let's go to settings. Go to control. Here we have a lot of settings here. Yes, we have a DOF. It's an averaging number. Here we use 120. Also, here we can select a clipping algorithm, window type for our data. We can select resolution lines. Also, we can use different control algorithms. We talked about them earlier. We can set the number of overlapping windows. We can set the error mass calculation. That means you can calculate it in full spectrum or task spectrum. And in that case, you can select the control process of your random test in many ways. We have a lot of options, a lot of different algorithms for controlling it. And I think we will add some new, and I think that's all settings you need, and they will cover all your needs.
All right. Thank you. So another one, how is the controller able to suppress the excitation at resonant frequency? And is it by varying drive voltage?
The drive voltage will be decreased on the resonance frequency. All the data from the sensors will be calculated, as I can say, in the controller. And if we get some resonances, we see that our voltage is increased, and we will check it and decrease the level on that frequency.
Yeah, also just wanted to add that there is where notching limits come to use, because they pretty much limit your acceleration at the certain level you set. So if you know that you have a resonance frequency on a certain point, you just set a notching limit there, and this will help you avoid damaging the system. I think that's all for the questions now.
And I think that I covered all most interesting features for newcomers. I made a quick start guide, and I think now you can use your system better. And let's make conclusions. Today we learned how to choose vibration controllers. We talked about our range of controllers. We described shakers, sensors for your needs. I told you about the basic vibration tests, the selection process of the sensor, the shaker. We made the first time assembly and installation, and I think I covered all your questions. If I missed something, we will answer it in the follow-up email. And I think that's all I wanted to say today about the basic vibration tests and this introduction webinar. I hope it was really interesting for you.
Yeah, great. Thank you. Thank you for coming, and thank you for joining us today. We will follow up with the emails in a few days. So I hope April was great for you. We just returned from ATE in India, and it was a blast. And thank you for your activity and your questions especially. Let's meet again in a few months.
Thank you for watching. Goodbye.
Bye-bye.